In this video, I'm going to explain how to solve the practical traveling salesman problem. This problem states that a salesman starts at one vertex. He must travel to all of the other vertices in the graph and return back to his starting point in the most efficient manner possible. The first thing that I'm going to do is I'm going to look at the weights of all of the edges and make sure that the weight for the direct edge is the minimum possible weight. I'm going to look here at vertex C and vertex D. I can see that the weight for the direct edge is 60. However, if I go from C to E and E to D, that has a weight of 25 plus 30 for 55. So the first thing I'm going to do is I'm going to change this direct edge weight of 60 to 55. The next thing I'm going to do is I'm going to turn this graph into a complete graph. That means that I want to make sure that between every pair of distinct vertices, there is a direct edge between those vertices. So next I'm going to connect vertex A with vertex E. And now I need to assign a weight. Now the minimum weight to get from vertex A to vertex E is 45 plus 25 for a total weight of 70. Next I'm going to add an edge between A and vertex D. And then I'm going to change the shape of this edge so that it's easier to see. And now I need to assign a weight for this edge. Now the shortest way to get from vertex A to vertex D is through vertex E. That's 70 plus 30 for a total weight of 100. Okay, now vertex A is connected with every other vertex in the graph onto vertex B. I'm going to add an edge between B and D. The shortest way between B and D is 35 plus 55 for a total weight of 90. And next I need to connect vertex B with vertex E. I'm going to adjust the shape of this edge so it's easier to see. And again, the shortest way to get from B to E is 35 plus 25 for a weight of 60. Okay, so now we have a complete graph with the Euclidean property. Next thing we're going to do is we're going to apply the nearest neighbor algorithm. So we're going to start by choosing our start vertex. I'm going to choose vertex A. Applying the nearest neighbor algorithm, I'm going to choose of all of the connected edges, I'm going to choose the edge that has the minimum weight that takes me to a vertex we have not been to yet. Choose this edge of weight 35, this edge of weight 25, this edge of weight 30, and now I've visited all of the vertices. I need to get back to vertex A, so I'm going to take this direct edge of weight 100. Next thing we're going to do is we're going to apply the deleted vertex algorithm. So I'm going to choose any vertex in the graph. I'm going to delete that vertex and delete any of the edges that are connected to that vertex. So let's delete vertex A. For the deleted vertex algorithm, we're going to find a minimum spanning tree by applying Kruskal's algorithm. So that states that at each step, I'm going to choose the edge of minimum weight so that we do not create a cycle. I'm going to choose this edge of weight 25, this edge of weight 30, this edge of weight 35. Okay? And then the next thing we're going to do is we're going to, of all of the edges that were deleted, we're going to choose the two edges that have the minimum weight. So here is this edge of weight 30, this edge of weight 45. And now we have completed an upper bound of 220 and a lower bound of 165, and that completes the practical traveling salesman problem.